post some info about that too. But.
Yeah, it worked.
Yes, it worked.
Bullshit day. You would know if you were here. Yesterday, but work with
Yeah, come on, man. Test. Cool. All right, how's everybody feeling?
Good.
Yeah, it's cold in here. I looked for a thermostat. I can't find anything, so we're a little out of luck. Sorry about it. But yeah, wear your hats. I see a lot of hats, and that's pretty cool.
I have a hoodie if anyone wants.
Sabrina's hoodie, up for grabs.
Yeah.
My coat, too.
Mine's better.
I vote we skip nomenclature for now, just because I think y'all are a lot more worried about the other parts of this exam, and we can double back and do nomenclature at the end. How's that sound? Yes? Okay, and that's what we'll do. Let's jump straight into facts then. Does everybody have a copy of the exam, or at least can look at it? It's on the ACS UH website. So if you just Google ACS UH, you'll find it right there. It'll be under practice exams. All right, so let's jump into the first one. Draw the tautomer of the compound below. So what kind of tautomerization has Dr. Bean been talking about? Keto-enol tautomerization. What that means. So you've seen some reactions that turn an alkyne into an aldehyde or a ketone. Let's go ahead and use a bigger one instead, just because I feel like it. What reagent is this, by the way? What reagent turns an alkyne into a ketone? Yep, HgSO4, H2SO4, and H2O. I had to check that one, but. Through this reaction, though, what you generate is called an enol. So first thing, you add this OH and it's immediately next to the double bond. This is called an enol. Enols are unstable. So even though this enol is the first product of the reaction, it's just an intermediate. It's going to immediately tautomerize into a ketone. Get comfortable with that conversion. So, looking at what we've got, draw the tautomer. What she wants you to do is to draw the other pair. So, looking at this first molecule, do we have the ketone or the enol? We have the ketone. So what do we need to draw? We need to draw the enol. Yep. So let's go ahead and draw our carbon skeleton, just all of our sigma bonds first. I'll go ahead and make this a little thinner. There we go. 2 carbons here, and we know we're going to have an O. And is it going to be O minus, OH? What's it going to be? OH, yeah. And there are 2 possible places, A and B, that the double bond could be. Where are you going to put it? Instinct kind of might tell you to put it on the more substituted side. So let's see what, let's see what happens when we put it on A. Let's just see what that looks like. What's wrong with that? Yeah, this carbon right here has 5 bonds now. Good or bad? Bad. So are we going to do that? Nope. Yeah, we're not going to do that. So we're forced to put the double bond there. And that's the tautomer. So with tautomerization, you'll have 2 tautomers, like a keto tautomer and an enol tautomer. Where is the equilibrium going to lie between these 2? To the left or to the right? To the left. She'll often ask you on exams where the equilibrium on this lies. the ketone is far more stable, and it'll instantly tautomerize to that, like 99 to 1. Any questions on that? Raise your hand, get your questions answered.
Is that because the C double O bond is more stable than the CC bond? Sorry, why does it lie to the left instead of the right?
I think it's entropy, if I remember right. Sabrina might have a better answer. Where are you at? Where is Sabrina?
Ionic mentioned that the CO double bond is more stable
Than the CC double bond with the OH next to it.
I think that's what
I'm curious whether it's stability or entropy.
I think it's in terms of stability, carbon-carbon double bonds are less stable.
Gotcha.
than the carbon-oxygen double bond because of the electronegativity of the oxygen.
Right, pulling that density up. That makes sense, yeah. So this CO double bond is a more stable double bond. This OH next to it, the oxygen being highly electronegative is going to pull some electron density out of that double bond, destabilizing it. And it's going to pull so hard, in fact, it'll actually just pull the whole bond over to itself. So it'll make that ketone instead. Awesome, let's move on. Place the alcohols in order of increasing reactivity in an acid-catalyzed dehydration. What reagent typically are we using in an acid-catalyzed dehydration? Typically, yeah, you're going to see H2SO4 and heat. Sometimes she'll give a specific temperature. H2SO4 and heat, that's where it is on your reaction sheet. The first step of that, in every case, is that the oxygen picks up another proton. What does that mean about charge? It's going to be a positive charge on all of those. It's going to pick up a positive charge on all of those. Because that oxygen now has to share electrons with hydrogen. So it lost some electrons in that deal. All of them are positive charges. What will happen then is that these will leave. So by protonating the OH, you've generated a good leaving group, and it's ready to leave. The next thing that will happen will be that it leaves on its own. It's going to be an E1-like reaction. So you'll end up with these carbocations. Which one of these carbocations is the most stable? The one on the far right, exactly. The one on the right is a tertiary carbocation. And remember, stability increases as substitution increases. So a tertiary carbocation is far more stable. So if this tertiary carbocation is the most stable, is it going to proceed through that reaction pathway easier or harder? Is it going to be harder to do that or easier? It's going to be easier. If it has a more stable intermediate, it'll more likely proceed through that reaction. Does that make sense? That intermediate is more stable. If it's less stable, it's going to require a lot more energy to get over the activation energy hump. Does that make sense? Cool. So this tertiary carbocation is going to be more stable, and it'll give us a lower activation energy. So this is going to be more reactive because it takes the least amount of energy to get over that activation energy hump. Likewise, the secondary carbocation will give us 2. Primary will give us 1. One thing I want to note, Dr. Bean, for the mechanism for the dehydration of a primary alcohol. Remember, the first thing that happens, we have our protonated alcohol, positive charge, and then that's going to leave. In the case of primary, it won't just leave on its own. It's going to accompany an immediate hydride shift to increase stability. That primary carbocation is extremely unstable. That said, this whole process still takes more energy than the others because initially it is the most unstable carbocation. So that's going to take the most energy to proceed through. Good or bad? Bad, yeah, you want a low activation energy. That'll make the reaction very easy to proceed through. Awesome. Let's move on. Number 3, place the compounds in order of increasing acidity. What's the very first thing you're going to do if you get a question about acidity? Draw the conjugate base. Deprotonate it. Yeah. Because then we can turn it into a question of stability. So let's go ahead and do that. We have this O minus with the NO2. We have this phenoxide anion right here. And then we have a substituted phenoxide. Let me actually go ahead and draw each individual double bond on this case. And we'll see why in a second. Doesn't matter where you put them. So, now our question is of stability, because acidity means that they're going from the original molecule over to the conjugate base. If it's an acid, it's going to have to donate that proton, right? It's going to go to the conjugate base. So now we're ranking that process. The way we rank that process is looking at the stability of our final product. So we're going to look at the stability of that conjugate base. Because if that conjugate base is more stable, it'll make that process easier. Therefore, it'll be more like an acid. It'll be more apt to donate that proton. So looking at stability, how about the left? Is there anything helping to stabilize that negative charge on the oxygen? No, it is isolated. So it's stuck on that oxygen. Good or bad? Bad. Yeah, that makes it pretty unstable. It makes it pretty reactive. It wants to react. So it probably will grab that proton back and go back to here, which is not good. We don't want that. Let's compare. Let's look at the second one. How about the second one? Do we see anything stabilizing that negative charge? Yes, the ring. Yeah, so let's look and see how that would go. We have 3 lone pairs on this oxygen, negatively charged. One of these lone pairs can hop down, forming a double bond with the ring. And that kicks that double bond out as an anion. I'm not going to do every single resonance contributor. I'm just going to show you the first one here to give you an idea of what's going on. What would happen is that this anion, that carbocation, is going to move from here to here to here. What that means is that you have 4 different atoms sharing the weight of that negative charge. Oxygen is going to take it on mostly because it's the most electronegative, but it has 3 other helpers. Good or bad? Good. Yeah, exactly. So is the middle one more acidic or less acidic than the first one? More acidic, exactly, because the conjugate base is more stable. So it's more likely to donate that proton and go to the conjugate base. Let's look at the third. Compare the second one and the third one. Which one has more stability? The last one. Let's actually draw out these resonance contributors. So initially they'll be here. You'll have your lone pairs here. This hops down. Remember, we said that the anion is going to form here, here, and here. We can go ahead and skip that, though. Because we see that normally NO2 looks like this. Negative charge on the oxygen, positive charge here. It can actually suck up a full bond. What that does is it kicks this pi bond out onto the oxygen, putting these 2 negative charges on the end with everything neutral in the middle of the ring. So that negative charge gets an extra oxygen to spread over. Good or bad? Good. Yeah, we want it to spread over as many atoms as possible, especially electronegative atoms like oxygen. Oxygen can carry the weight. That's way better than carbon trying to carry the weight. So, between the middle and the right, which one is more stable? The right. Yeah, the conjugate base on the right is more stable than the conjugate base in the middle. So, is the far right going to be more acidic than the middle? Yes, the conjugate base is more stable, so it's more acidic. This is the most acidic, 2 and 1. Awesome. If you have any questions, please raise your hand. All right, this is an essay question. So Dr. Bean, sometime in Orgo 1 or 2, for me it was in Orgo 2, will put an essay question in one of her exams. It'll usually be a midterm exam. What you're going to have to do, really carefully read the directions and make sure to address every single piece of what she says in her directions. Read the directions very carefully. So let's go ahead and do that. Although the product of an alkene and HBr with peroxide is described as a non-Markovnikov product, the reaction follows the general principle of Markovnikov's rule. Explain. That's tricky. It requires you to know the mechanism. I actually want to go ahead and draw out the mechanisms for these. So the directions say the product of an alkene with HBr and peroxides. We'll just use hydrogen peroxide. Make it easy on ourselves. You're also more than welcome to put R groups here. That's fine as well. Let's also look at what happens when you don't put peroxides in here. Just regular HBr. So let's actually start with HBr. So what's going to happen first? Your double bond. Is your double bond a nucleophile or an electrophile? It's a nucleophile. Yeah, it's got some extra electron density that it can use to attack. Out of these two atoms, H and Br, which is the electrophile? It's going to grab the hydrogen. Yeah, the bromine is going to be hogging most of the density, so that hydrogen, partially positive. So this double bond is going to grab, I used a bad example of an alkene. Let's put 2 R groups here, 1 R group here. It's going to go ahead and grab a hydrogen. We have now 2 options. We can put the hydrogen here, say on carbon A, and leave the positive charge at carbon B. Otherwise, we could put the hydrogen in carbon B, which leaves the positive charge on A. Which one will we choose? This is without, so this is just HBr. All I'm asking, so just which of these is more stable? Which are we going to choose? The left one, yeah, so we're going to choose the one on the left because that puts this positive charge on a tertiary carbon. So it's going to be a tertiary carbocation. On the right, we have a secondary. And this is the real essence of Markovnikov's rule. What he really says, the extended Markovnikov rule, is that the reaction will proceed through the most stable intermediate. So let's go ahead and finish this reaction. We decided that we're going to go with the left. Bromine, Br minus, is going to be our nucleophile. This carbocation is a great electrophile, so this Br can come in and attack here. And we end up, I'm going to not draw the hydrogen just to keep it line angle. We end up with a Br on the most substituted carbon. So that's a mark addition. But we proceeded through the most stable intermediate. That puts the Br on the most substituted carbon. Let's contrast now the reaction with peroxides. The very first thing that happens here is that a radical is generated. So it has a different first step. So single-sided arrows. This peroxide is going to bust open, 1 electron on each. So you'll have this radical right here. What that's going to do, it's going to go ahead and grab the hydrogen and form a bond. 1 electron each. Hydrogen is going to contribute an electron of its own. That means 1 electron is left for the bromine. So that first step with peroxides generates a bromine radical. That's crucial. Now, this bromine radical is our electrophile. We have a new electrophile now. So before, we added hydrogen first, and we put it on the side that was going to give us the more stable intermediate. Now we're adding bromine first. So we've switched the order that we're adding them in. So we've got our alkene, and we've got our bromine radical. One of these is going to link up with the bromine radical. Where is the other electron going to go? Is it going to go on carbon A or carbon B? Where will it be more stable? Where is a carbon radical most stable? On a tertiary site. You want that radical on a tertiary site. So that extra electron is going to hop off and go over to the more substituted side. So let's look at this intermediate. We're not done with the reaction yet. We've added a Br here where we added the hydrogen before, and now we have this tertiary radical, which is the most stable intermediate. And that is Markovnikov's rule. That still is following it. So we've proceeded through the most stable intermediate. So we actually still are obeying Markovnikov's rule. What we end up with, more HBr in solution. This is going to grab a hydrogen. Sorry, that's not quite right. Going to grab a hydrogen, one electron each, and you're going to generate a new bromine radical. So then you end up with the bromine on the non-mark side. So with respect to the bromine specifically, the first reaction, put it on the Markovnikov side. The second reaction, put it on the anti-Mark side, the non-Markovnikov side. So let's go back up to our essay question. Now we know what we need to know to answer this thing. Although the product of an alkene and HBr peroxide is described as a non-mark product, the Br adds to the less substituted side, that's what that means, the reaction follows the general principle of Markovnikov's rule. Explain. So the first thing we're going to say is that the bromine radical will add first. Sorry, guys. We coming back? There we go. Sweet. Sorry about that. So this places a carbon radical. I don't like the way I said that. Let's change that. The radical generated will be on the more substituted carbon following the principle of Markovnikov's rule. Any questions on that? To see what she said, make sure I address everything. Yep, that's it. Any questions on that? Awesome. Please raise your hands if you do. We can talk about them after too, just kind of like the ins and outs of how to respond in word form. Typically, they'll be about theory. They'll be about mechanisms. Awesome. Number 5. List 3 methods for converting an alcohol functional group to a good leaving group in SN2 or SN1/E1 reactions. So we're going to convert an alcohol to a good leaving group. And there are a few ways we can do that. Let's look at what we've got to start with. So let's just say, right here. Currently, it's not a good leaving group, is it? What's one way we could make it a good leaving group? Protonate it. Yeah, that's one great way to start. So our first method would be acid catalysis. That's kind of a fancy way of saying that we could use like acid catalyzed dehydration to turn the group into H2O plus. So we've added that positive charge on there. Is it good? Is it a good leaving group now? Awesome. So that's one method by which we could do it. What's another way we could do it? Yeah, we could make a tosylate anion. So that tosylate anion makes the O very bulky. It also stabilizes those electrons as they go off onto the oxygen. That's another method we could use. So the generation of a tosylate group. Is that going to switch stereochemistry or not? So if you use TSCl and pyridine, say this OH were on a wedge. Is this going to be on a wedge or is it going to be on a dash? It's actually going to be on a wedge. You'll have a retention of stereochemistry. So keep that in mind for the reaction section. We'll need that later. There's one more way. We could convert it into an entirely different functional group. We could turn it instead to an alkyl halide. So another way, convert to alkyl halide. With, for example, PBr3. And that would just turn it to a bromine. Are there any limitations with PBr3 as a reagent? Can we use it on every type of alcohol? No, yeah. You can only use PBr3 for primary or secondary only. The alternative, what you're going to do, say you have this tertiary alcohol, and you want to convert that to a tertiary alkyl bromide, you would use HBr in ether at 0 degrees Celsius. That's your alternative for a tertiary. So just keep that limitation of PBr in mind. Awesome. Those are the primary 3 methods. Any questions on that? Raise your hands. Let's move on to our favorite section, the reaction section. We can post this as well. Do you want this fact section? Okay. Awesome. Let's go ahead and jump right in. This first step is actually combined with the second step. This is our hydroboration oxidation. What functional group are we going to generate in this process? We're going to add an alcohol. Yes, we're going to add an alcohol to this thing. With boron, is that going to be the Markovnikov side or the anti-Markovnikov side? Anti-Mark. Exactly. So is that going to be on carbon A or carbon B? Carbon B, exactly. Yep, it's going to add to the less substituted side. And that is our steps 1 and 2. You don't need to write the product of step 1 and then the product of step 2 in this case. Those are a pair. We just talked about this one. PBr3 is going to convert an alcohol into a what? Yep, an alkyl halide. In this case, alkyl bromide. Could we have used that on a tertiary alcohol? No, you would have to use your HBr in ether at 0 degrees Celsius. That's the alternative. This next reaction, it's not very well understood. It's called the Corey-House reaction. And it is another way of generating carbon-carbon bonds. The mechanism isn't really all that well understood, so I'm just going to show you how it works. Let's go ahead and draw a product here. It's going to rip the bromine off, and it's going to add one of these two R groups here. So C number 4. So this is Corey-House. You're going to add one of those two R groups. In this case, it's an ethyl group. So in the place of this bromine, we're going to add 2 carbons. Let's go ahead and put them in red. 1 carbon, 2 carbons. So notice you only add one of the 2. The mechanism is not very well understood. Both the book and Dr. Bean say that, so you're 100% not responsible for that. That is just memorization. Awesome. Let's move on. So lithium aluminum tetrahydride. What this looks like, the lithium is a spectator ion, and you've got the aluminum connected to 4 hydrides. This aluminum is going to have a negative charge. These bonds between the H and the aluminum, they're nucleophilic bonds. They're similar a little bit to Grignard. So what this nucleophilic bond is going to do is going to attack the backside of the carbonyl and pop one of the lone pairs up onto the oxygen as a negative charge. So as an intermediate, we'll get this. I'm going to erase some of this mechanism later, just a heads up. So we have this oxygen pair with what kind of a charge? Negative charge. Yeah, we created a negative charge on this thing. So we've got a negative charge. We're still connected to this oxygen with the ether, and we've added a hydrogen to the carbon that originally was the carbonyl. If this weren't an ester, this is an ester. If this weren't an ester, if it was just like, say, a ketone, it would be done and it would wait here. It would stop until you added H3O+. It would just stop. In this case, though, because it's an ester, we have a good leaving group. This, on the end, the ether over here, is a good leaving group. So what can happen? The pair of electrons, the negative charge, can come back down, regenerate your ketone. In this case, now it'll be aldehyde. And it'll break that bond, hopping that pair of electrons over onto the oxygen. So that's going to cleave it open. That's going to cleave your ester open. But what you generate, you have an aldehyde. See, because you regenerated your carbonyl. And on the right, we're going to have an alkoxide. So that's kind of the first general step. There's more. The lithium aluminum hydride can still react with that aldehyde. So another hydride, let's just use a fresh one. You can use all 4 equivalents. All 4 of these hydrides are good. So you could just use 3, and that would be fine too. Let's just use a fresh one. Again, this hydride can come attack the backside of the carbonyl, kick that bond up onto the oxygen, and you generate an alkoxide. Negative charge up there, right? Are we done now? Almost. We're almost done. We're really close. We would just add then H3O+. We are done with the lithium aluminum tetrahydride, though. There's nothing more this can do. Nothing else can be reduced. So we are stuck now that everything is an O-. So then you just protonate these guys. What do you notice about those two alcohols that we generated? This guy and this guy. They're the same. Yeah. So when we cleaved that thing open, we generated two identical alcohols. Does that make sense? The process to get to each one was slightly different, but at the end of the day, they were both the same alcohol. I'm going to go ahead and erase this mechanism if you want to take pictures or anything. Cool. Okay. If you have to, do that on your exam. Don't leave it on your exam, but you can go ahead and kind of write the mechanism to get yourself through it, if that's going to help you. We have this alcohol. We said they were both identical, so we could even say to equivalence if you want. You don't even have to. You can just put the alcohol. They're both the same. So, POCl3 with pyridine. What's going to happen with that? We're going to form what kind of functional group? This is going to form an alkene. This is a dehydration reaction. Is it going to form an internal alkene or a terminal alkene? This one is going to be a terminal alkene. What would you do if you wanted to make an internal? Instead, on your arrow, you would have H2SO4 and heat. If you wanted the internal alkyne, the more stable one. POCl3 adds to the very end, and so it's restricted to making the alkyne at the very end, terminal. I'm not going to go through the whole mechanism on that one. But you generate that terminal alkyne from step 2. This was step 1. Step 3. These two reagents together form a carbene. So what that's going to look like, you'll have a carbon, electrons here, Cl, Cl. It's neutrally charged, but it doesn't have a full octet. So it's very reactive. I'm not going to show the full mechanism on this one either. What's going to happen is that that carbene is going to add to your double bond. It's going to add to your alkene, and you're going to make cyclopropane. And whatever's on your carbene will stay there. So let's go ahead and draw that. We'll have a cyclopropane. What was here? Are we going to have hydrogens here? Or what was originally on there? Chlorines. Yeah, you're going to have chlorines on there. And that's it for that one. If you have questions, raise your hand. People will be coming around to answer. Awesome. So we just talked about this one, H2SO4 and heat. Notice something. We have a specific heat given, 180 degrees Celsius. There is a reason for that specific one. A lot of times she'll just put heat. This is important. Notice here what we have on our first reagent. We have a primary alcohol. You need very specific conditions in order to dehydrate that primary alcohol. So you actually need to put 180 degrees Celsius if you want to dehydrate that primary. We just said, is it going to make a terminal or internal alkene? Internal. So this is going to rearrange. You're not going to have your double bond here. It's going to go one further. It's going to rearrange to be internal, the more stable alkene. Awesome. Second step, Br2, and this is DCM. She may write it as DCM, dichloromethane. What that's going to do is it's going to add Br across the double bond. Both Brs will add. It proceeds through a bromonium intermediate. So you'll have a cyclic intermediate with bromine in there. And the second bromine will come and backside attack it. It's similar to the epoxide opening. What you'll end up with is a vicinal dibromide. Step 3, KOH 200 degrees Celsius. There are, how do I want to say this? This reaction generates an alkyne, a triple bond. It'll do E2, 2 times consecutively. There are 2 possible reagents you can use for this. So let's just go ahead and draw our whole thing. So our first reagent, KOH at 200 degrees Celsius. This, is it going to generate an internal alkyne or a terminal alkyne? Internal. It's going to generate an internal alkyne. Is internal more or less stable than terminal? Internal is more stable. We're going to talk about that in a second. So that's going to be an internal alkyne. If you used sodium amide, NaNH2, at 150 degrees Celsius, is that going to generate an internal or a terminal? Terminal, exactly, yeah. So we're going to have this CH2 connected to a C, triple bond to a C. Are we going to have an H at the end there? Initially, yes. So initially, yes. But what this is going to do, this reaction will continue under the same conditions, same reagents. To give you this acetylide anion, or acetylide-like anion. You don't need to write both of those consecutively like that. See how I have the first NaNH2 and then the second one? Don't do that. Just write the product of both steps because it happens under the same conditions with the same reagents. So this is going to be followed by a deprotonation. We said that this internal alkyne was more stable, correct? So why would we want this terminal alkyne? The reason is the sodium amide, the NH2 minus, this is a very, very strong base, much stronger than OH minus. So what that's going to do, it's going to really, really want to deprotonate something. So there's an equilibrium where this triple bond can shift. One of the bonds moves and then the other bond moves. So you end up with 2 double bonds next to each other at a time, and then one hops over to make the triple bond. If you have this NH2 in the solution, it's going to have a really strong desire to deprotonate that terminal alkyne. Can it deprotonate anything? If you put NaNH2 in this, can it deprotonate anything? No, it can't really deprotonate anything. So it would actually catalyze a rearrangement to put the alkyne at the end so that it can rip the proton off. That's the driving force. It wants to rip that proton off. So a few of you were asking why this happens yesterday. This is why. So those are the 2 different possible ways you can go to generate alkenes from these vicinal dibromides. It also works with geminal dibromides, which looks like this on the same carbon. But let's go ahead and stick with what we had before, vicinal. So, again, real quick, now that you can't see it, KOH is going to generate terminal or internal? Internal, yep. So we're going to generate an internal alkyne, triple bond. All right, this is getting a little long on this one. Step 4. This is lithium metal. This is not charged. Lithium metal in liquid ammonia. What this is going to do, it's going to solvate electrons and cause a structure that has a single electron on one side and then a lone pair sticking up on the other. It's going to eliminate one of the bonds. You'll end up with a single electron here and 2 electrons on the other side, and they get repelled by each other. They're electrons. They're all negatively charged. So they get repelled by each other, so they're going to want to be on opposite sides. And then you fill those gaps later. I'm not going to do the whole mechanism, but you'll fill those gaps later with hydrogen, and they'll be on opposite side. So with this reaction, you're going to generate a trans double bond. So this alkyne is going to be reduced to an alkene, and you're going to generate a trans double bond. It's not going to be cis. So we're going to have, say we pick that side for the first hydrogen. We're going to have a double bond. We have A and we have B. Are we going to put hydrogen on A or B? We're going to put it on A because we want it trans, remember? So it's going to add those hydrogens opposite to each other. Then our last CH3. Awesome. So we've generated that trans double bond. What if you wanted to generate a cis double bond? What would you use instead? H2 and Lindlar's catalyst. So instead, your step 4 would look like this. H2, it might be Lindlar's catalyst. She may also write out what Lindlar's catalyst is. So be ready for that as well. That would be H2 with palladium, but you're going to poison it with barium sulfate. And that's going to be in quinoline as a solvent. That's Lindlar's catalyst. That would give you a cis double bond because the protons will, or the H2 will all be sitting on the catalyst and it's got to come in and grab them. And so one of the sides of the molecule is going to have to grab both. It's going to have to hit the catalyst and grab both and leave. So the hydrogens will end up on the same side. So that'll give you a cis double bond. But we don't have that. We have the trans double bond formation. All right, step 5. This should be familiar. What does MCPBA do? Forms an epoxide. Yeah, it's going to form an epoxide across that double bond. So it's going to break open that double bond and make an epoxide. Drawing stereochemistry for epoxides. It does matter. Let's just start with our epoxide itself. It's useful to put the epoxide, the 3-membered ring, in the plane of the page. So don't try to put these on wedges or dashes or any of that. It's a humongous pain. Don't try it. So here's what we're going to do instead. We're going to put our epoxide in the plane of the page. This guy, that means we're going to have to rotate it 90 degrees. We're going to have to be either looking down at it or looking up at it. So what that means, we're going to have to pick, we can just look at this hydrogen and this cyclohexane. Which one of those do we want to be in front? Let's put the cyclohexane in front. You can pick because either is going to be fine. We just have to stay consistent. So let's put our cyclohexane at the front. What that means is that this hydrogen is going to have to be in the back. So now we've decided what direction we want to be looking at this in. We're going to look at the other side. Which hydrogen or CH3 are we going to want in front? We're going to want this hydrogen in front. See, we decided the cyclohexane was in front. That means this hydrogen has to stay on the same side. The stereochemistry gets preserved here. So it doesn't rotate in the process. So this cyclohexane and the hydrogen have to be on the same side. They're both going to be in front, which leaves the CH3 in back. That's that for that one. Raise your hand with questions, and someone will come around for sure. Moving on. All right, so this is our mercuric sulfate. We talked about this earlier. It's going to turn an alkyne into what kind of functional group? What are we going to get? We're going to get a carbonyl-containing compound, in this case, a ketone. With mercury in it, are we going to add that ketone to the Markovnikov side or the anti-Markovnikov side? Markovnikov, the more substituted side. So looking at our alkyne, we have carbon A and carbon B. Which one of those is more substituted? A is more substituted. B is the terminal end, so it's just one carbon there. If we're adding to the Mark side, we're going to want to add that carbonyl to carbon A. There's no double bond left over. Initially, there is a double bond. That's actually something we just talked about. So I'm going to put this in line angle just to make life easier. Initially, we formed this. What is that? It's an enol. What did we say about the stability of that enol? It's unstable and it will tautomerize to the ketone. So that's where that ketone comes from. It goes from a triple bond to a double bond and adds the OH next to it, but it's so unstable that it immediately switches over to the ketone. So we end up with our ketone. I'm going to go ahead and convert this into line angle since we're about to do some Grignards. That's a useful thing. So I don't love structural formulas. It's a little harder for me to look at. So I like to just convert it to line angle. That's the product of our step 1. Step 2, we have a Grignard reaction. So this is a carbon-carbon bond forming reaction, right? So where is our nucleophile here? That's important to know. So it's the bond between the carbon and the Mg. That's our nucleophile. MgBr afterwards will just leave as a salt. This bond is going to come attack the backside of our carbonyl, our electrophilic site. That's going to kick one of the pi bonds up onto the oxygen, generating what kind of charge? A negative charge. You're going to generate a negative charge here. So we'll say sort of like a 1.5. No, I'm not going to do that. Initially, you generate this O minus, and you have a new carbon-carbon bond that's formed, right? And what's going to be attached now? A new cyclohexane ring. That was what was attached to our Grignard. So we're going to form a new carbon-carbon bond between the cyclohexane ring and the back side of the carbonyl, the carbon in the carbonyl. So that's initially what we're left with, and it stops there until you add aqueous acid, H3O+. That's going to provide a source of protons to protonate this. Awesome. That's step 2. Step 3, HBr, ethers, 0 degrees Celsius. We talked about this one, didn't we? Remember, that was the alternative to PBr3. So remember, they're kind of diametrically opposed. This, HBr, ether, and 0 degrees, is it for primary, secondary, or tertiary alcohols? Tertiary. This is what we use when we want to convert a tertiary alcohol to a tertiary alkyl bromide. So we're going to replace the oxygen with a bromine. 2, 3, 4. Br with our cyclohexane ring. That's it for that one. Moving on. Please ask questions. Okay. Interesting. We're given the initial compound and the final product, and we have to write down the reagents. So, like a synthesis problem, this is kind of a synthesis problem. This is forward synthesis. We're going to need to kind of make a game plan here. So, we're given some stereochemistry. Do we see it inverted or do we see it retained? We see it inverted, right? So our OH is on a wedge in front. It's sticking out in front. And that cyanide at the end of the day is in the back. So what kind of reaction inverts stereochemistry? SN2, yeah. So you're gonna do an SN2 reaction on this thing and invert the stereochemistry. Is this OH at the beginning, is it a good enough leaving group to just SN2 that right off? No. Yeah, you can't do that immediately. We talked about earlier some ways to make OH a better leaving group. What were they? Protonate the oxygen, turn it into a Br, or turn it into OTOS, turn it into the tosylate anion. What did I say about the tosylate anion? Does it invert the stereochemistry when you add that tosylate? It doesn't. That's very useful. Does it invert the stereochemistry when you use PBr3? Yes, it does. So if you wanted to use the method of converting it to an alkyl halide, you'd end up with your hydrogen on the wedge, bromine on the dash. So now this is good for SN2. But if you did SN2 here, what would you get? It would invert. Yeah, it would invert. So you would end up, so say you used NaCN on this. You would end up with the cyanide on the wedge. Hydrogen on the dash. Is that the product we need? No. Yeah. So you should be able to think that far. Be able to think that far and be like, okay, if I do PBr3, it's going to invert the stereochemistry, and then I won't be able to do an SN2 properly. Does everyone see that? So this is an SN2. So that 100% inversion. And then this is another SN2. So you're going to have another 100% inversion. If you invert it twice, what do you get? A retention product. Yeah, did we want the retention product? No, we want the inversion product. So we're going to need to choose a method of making this OH a good leaving group that doesn't compromise that doesn't do that SN2 reaction at the very beginning. We only want one inversion. So let's erase this. This was incorrect. Don't do that. So what way could we use to make the OH a good leaving group without switching the stereochemistry? Tosylate, yeah. I'm not sure if you need to put the P. It's paratoluene sulfonyl chloride is the compound, but sometimes she'll put the P, sometimes she won't. It doesn't mean anything. It's the same compound. What does she want you to put this in? Pyridine, yep. Memorization on that one. What that's going to do is it's going to add a tosylate group to our oxygen, the one in the alcohol, without inverting stereochemistry. It's going to retain stereochemistry. So retention, right? So now we want to invert, right? And SN2 will do that for us, right? So we're just going to do an SN2 reaction. NaCN, cyanide is our nucleophile. What is a good solvent for NaCN, for an SN2 reaction? Yeah, you want a polar A product solvent, so DMSO is a good option. There are a few you could use. Let's just use DMSO. So initially we have the retention. On the second step, we have 100% inversion. If we invert 100% one time, are we going to have inversion or retention? Inversion, yeah. So you're not going to cancel it out. So does everyone see how this method is better than the one with PBr3? Just keep the ins and outs of this in mind, because she may ask you to do it either way. In this case, she's asking you to do the inversion product. She may want the retention product. So in that case, you would want to do the double SN2. So invert it and then invert it back to the retention product. If you have any questions about that, raise your hand. Awesome. Here we go. An alkene with cold KMNO4. If we used hot KMNO4, what would happen? It would cleave that double bond. It would generate carboxylic acids and, in this case, CO2 and water, since this is terminal. So it would generate CO2 and water from that, and this would be a carboxylic acid. That's if it's hot. So keep in mind that cold and hot have completely different reactions. What the cold KMNO4 is going to do, it's going to prevent it from oxidizing it quite as much, and you're going to generate syn-diols. You don't need to put this stereochemistry here because there's free rotation. If you had it on a ring, if you had it right here and you used cold KMNO4, you would need to show syn stereochemistry. So you would want to show, you could pick wedge or dash, but show them both on the same side. It'd be a syn addition of those OHs. So it'd be a syn-diol. In this case, since it's a straight chain, there's free rotation around these bonds. So we don't have to show the stereochemistry there. Awesome, we have that syn-diol. That's step 1. Step 2, dichromate. This is similar to what reagent? Jones. Yeah, it's going to be similar to Jones, which is the CrO3. It's a strong oxidizing agent, so it's going to oxidize both of these. 1 to a ketone, 1 to a carboxylic acid. Awesome. Step 3, NABH4. Is it selective or unselective? It's selective. Is it a reducing agent or an oxidizing agent? It is a reducing agent. Yeah, both of these are already pretty oxidized. We just used a strong oxidizing agent, so they're going to be pretty oxidized. Now we want to reduce it again. Or at least that's what she's telling us to do. So we're going to use this selective reducing agent. This will reduce aldehydes and ketones. So looking here, do we have any aldehydes or ketones? There's a ketone on the left. Did I include carboxylic acids in that list? No. So is it going to reduce that carboxylic acid? No, it's not strong enough. It's weaker. What would be the stronger counterpart? LiAlH4. It's very similar. Remember how the mechanism was initially with the aluminum? Very similar. When you use the boron, it's slightly weaker. The hydrides aren't as strong. So if you want to reduce everything, LiAlH4, that's very unselective. It'll just reduce basically everything. So we said we are going to reduce the ketone to an alcohol, and we're not going to have the power to do anything to this carboxylic acid. If you have any questions, raise your hand, and someone will definitely come around. All right, mechanisms. Definitely, you want to be making a game plan. Another very useful tool that's going to help you a lot. You can number these things, and that would help a ton. You don't have to do nomenclature-style numbering. What I'm going to do, I'm going to pick some arbitrary numbers for these carbons, and I'm going to put them on places that I want to keep track of. So I want to keep track of that carbon right there. I want to keep track of this quaternary carbon because it looks like a very recognizable site, right? Like you'll be able to see those 2 methyl groups sticking out somewhere on your product. So that's a recognizable site. We'll call that 1. Looking at our product, where do we see those 2 methyl groups jutting out? On the left side, right here. So these are the same carbon. Those are also carbon 1. Does that make sense? Awesome. This will be really helpful because the skeleton is going to change shape, especially with these ring formations, and you'll form some new carbon-carbon bonds. So let's go ahead and number down this thing. 2, 3, 4, 5, 6. Okay. Here's something for you. We have an epoxide on carbons 1 and 2. Looking at carbon 1 on the product, do we have an alcohol anywhere? No. So where would this epoxide have gone? It's going to turn into an alcohol, right? When you open it, it's going to turn into an alcohol. So is this carbon 2 or is this carbon 2? Top or bottom? The top, right. The top is going to be the one that used to hold the epoxide. So we need to make sure to number that direction. So let's go ahead and number these 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's immensely helpful because now we can keep track of every carbon. The other thing that we can see is in our original reactant, there's no bond between carbon 1 and 6. See how in the product we have a bond between carbons 1 and carbon 6. What does that mean? That means at some point we're going to have to form the bond between carbon 1 and 6. Looking at carbon 1 and 6, which one is going to be the nucleophile? Carbon 6. Yeah, carbon 6 at some point in the mechanism is going to come attack carbon 1. Does that make sense how I got that? So we're kind of deducing a lot of the things that are going to happen before we even do it. That's very helpful to kind of give yourself a game plan, take a second and look at it and think about it. Give yourself those numbers. It'll help you a lot. Just want to reemphasize, these are not numbers for nomenclature. So if you were numbering this for nomenclature, you would have to do it properly following IUPAC. This is just numbers for us to keep track. Just a tool for us. So we have an epoxide opening. One thing I want to talk about with an epoxide opening, there's an acronym that should be really helpful. You may have already heard it, but it's BLAM. Pretty easy to remember, right? BLAM. What that stands for, basic, least, acidic, most. What that means, when we use a nucleophile to attack our epoxide, if we are in basic conditions, that nucleophile will attack the less substituted side. If we're in acidic conditions, it'll attack the more substituted side, the most substituted side, BLAM. So just remember BLAM, basic will be the least, acidic will be the most. And that is for epoxide opening only. So let's look at that. Are we in acidic or basic conditions? We're in acidic conditions. Yeah, we have this H plus here. So that's acidic conditions. The first step of the acidic epoxide opening, and this you have to know, is that the lone pairs on the oxygen in the epoxide will grab a proton. In this case, she left it floating out in solution. If she gave you like HOH2 with the positive charge here, you would need to show that bond hopping onto the oxygen. In this case, we can just go ahead and grab it because it's not bound to anything, so we don't need to break bonds. So first step, we're going to protonate this epoxide. That's going to make it much more reactive. It's going to make it much more apt to open it. It's going to be ready to be opened. Because if you backside attack, say you attack there just because, it would make it a great leaving group. Let's look here, without even looking at our numbering, what side, carbon A or carbon B, is going to be attacked. Remember BLAM, right? Are we in acidic or basic conditions? Acidic, so are we going to attack the more substituted or less substituted side? The more, so AM, acidic most, so we're going to attack the most substituted side. Double checking our work here, we can see that we need to form that bond between 6 and 1 anyway. So that's just a good way to check our work. We know for sure that we're doing it right because it follows the theory behind it. Like this nucleophile is going to attack the more substituted side. So what that's going to do, that pair of electrons is going to come attack the epoxide at the most substituted side. What that's going to do is it's going to break the carbon to oxygen bond in the epoxide. That means the OH is going to swing out, as in, it'll be an OH in this case. So now we formed a new carbon-carbon bond and we've closed up this ring. So we're going to have to redraw it. I recommend go ahead and look at the product and draw it just like she did and number it later. Just go ahead and draw for now. You don't even have to make sense of it yet. So we're not going to put this ether or the double bond in there yet. We're just going to leave the carbon skeleton and we're going to take stock of what we have. Looking at our product here, let's go ahead and number this thing. So we see this has to be carbon 1. I'm going to change so it's a little more clear. That has to be carbon 1, 2, 3, 4, 5, 6, right? That's how we numbered it in the beginning. The reason to do this is steps like this. So now you can number this thing again. 1, 2, 3, 4, 5, 6. And it can show you where everything is going. So the OH that results from this, is it going to be on carbon 1, 2? Where's it going to be? It's going to be on carbon 2, see? Because when that epoxide opened, it kicked the OH over onto carbon 2, exclusively onto carbon 2. It broke the bond between carbon 1 and the oxygen, and it swung open. Now it's just on carbon 2. So we have an OH here. which we can check our product. That is consistent with our product, so we did it right. We're good. Is that all we have here? Is there anything left over? Positive charge here. It was there. I think I erased it. But there's going to be a positive charge here. Remember that conservation of charge. That charge didn't just randomly disappear. So looking at carbons 5 and 6, this double bond left. So somebody lost electrons in that deal, right? If the double bond is gone, some electrons went missing. So did carbon 6 lose any electrons? No, yeah. It used those electrons to go attack carbon 1, and it's sharing them with carbon 1 now. So it still has ownership of those electrons. It didn't really lose anything. Who did lose something? Carbon 5. Yeah, so carbon 5 is what's going to have that positive charge on our molecule that we just made. So let's go ahead and number it. I erased them, sorry. 1, 2, 3, 4, 5. Carbon 5 has our positive charge. So this process, going to that step, is probably the trickiest part, formation of that ring. That's why I recommend the numbers. It's a really helpful tool. It's just going to kind of keep you on track so that you don't lose track of which carbon was which before and after that ring closure. So here's what we've got. Looking at our products, so carbon 5 here, it's a very reactive site. Do we see anything adding to carbon 5 or a double bond forming at carbon 5? No. So are we going to need to move that electrophilic site somewhere? Yes, we're going to do a hydride shift to move that electrophilic site somewhere else so that it's consistent with the product she gives you. So our next step, there's two ways to check this work. First is just theoretical. Which hydride is going to move? Hydride A or hydride B? B. Why B? It'll give you a tertiary carbocation. If you went with hydride A, you would still have a secondary carbocation. You didn't gain anything from that. So why would you do a hydride shift? It did nothing for you, so it wouldn't do that. So it's only going to shift from hydride B. So hydride B will come fill that carbocation, generate a new carbocation on our tertiary site. Looking at our products too, we can also see that we're going to need to do a substitution on carbon 4. So we're going to need carbon 4 to be a good electrophilic site. So if you know the theory, great. If you don't, you can always look here and see what you need to make. So if you forget, there are ways out. So we're going to move that hydride B over to the secondary carbocation, and that will generate a tertiary carbocation. Positive charge in there. Our hydride moved here. So now we have a great electrophilic site on carbon 4. Let's look at our first product, product A. What happened? What's new on carbon 4? We have this OCH3 group there. There's a substitution happening, and it's going to be an SN1 because of this carbocation. It won't be SN2 because we've already kicked out the group. We've generated that carbocation already. So what do we have that we can work with? CH3OH, or methanol. Can we use methoxide? What do y'all think? Can we use methoxide? No. So first reason, the most obvious reason, is that we're not given methoxide. So that's the first reason. The other reason is, think about this. We're in acidic conditions. Would methoxide exist in acidic conditions? No. So yeah, there's two reasons why we can't use that. So we have to use methanol. One of the lone pairs is going to come attack the carbocation. that results in this, right? Are you sure? What are we missing? There should be a hydrogen there. Yep, we never got rid of that yet. So see this hydrogen on the end of the methanol? We didn't get rid of that yet. So don't just like throw it away and pretend it doesn't exist. You do have to show where that goes. What does that mean about this oxygen? Positively charged. Yep, it still has a positive charge on that. Another methanol can come by, grab the proton, deprotonate, put those electrons onto the oxygen, and that leads to the formation of product A. Let's erase some of this craziness. So that got us to product A. Let's go ahead and do a redraw for this. So we got our carbocation back. Just signify it in a way that makes sense. They're not super picky. So saying I'm redrawing that. So what do we need to do? So we formed product A. We need to form product B. We have a double bond now, right? We formed a double bond between which two carbons? 3 and 4. Yeah, so we have our positive charge already on 4. Are we going to take HA or HB? HB. Yeah, if we took from HA, you would form the double bond in the wrong place. It's possible she may ask you to use HA, but you have to look at the product to see for sure. You have to see which way that double bond is going to go. So even though these are more or less equivalent, you need to do what she says. So pick B. A methanol, using its lone pairs, can come abstract this proton. The electrons in the CH bond they're gonna break, or the bond will break, and the electrons from that bond will form your double bond. It'll flow towards that positive charge and resolve it. Charge is conserved. Where did the charge go? Onto the methanol. So you don't need to show it anymore because it left with the methanol. It is conserved, but it left. So that leads us to the formation of a double bond, and we're done. If you have questions about this or how to navigate this, raise your hand and get some help. We can also talk after too. Awesome. Synthesis. Synthesis is my favorite. It's really fun. It's what made me like Orgo. Also, just if y'all are discouraged, I liked Orgo 2 way, 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 way more than Orgo 1. So if you're not feeling this right now, you might like it later. So if it feels terrible right now, give it a chance next semester. Okay, so we need a game plan, right? We're not just going to jump straight into this. First thing to do would be to look at what we're allowed. I see cyclohexanol and alcohols or alkynes of 3 carbons or less. So does that mean we're allowed alkanes? No. So if you went back to an alkane, would you be wrong? Yes, you would. So don't go back to an alkane. You're used to doing that. Don't do it. Make sure you're allowed alkanes if you want to do that. It's actually easier to just stop at the alcohol, though, or alcohol or alkyne. Okay, so the other thing we need to see, 3 carbons or less. How many carbons are in this guy? I mean, we have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I mean, we have to break this up, right? This is too long. We are allowed cyclohexanol, so this amount of carbons is fine. We need to look at the left, though. How many carbons are on that left piece? 4. We have 4 carbons. Are we allowed 4 carbon compounds? No. So are we going to need to break somewhere in there in the middle? Yeah, we're going to need to either break here, here, or here to give us pieces of 3 or less. That's in addition to the fact that we know we have to bust that off. We already know that because we're allowed cyclohexanol, but not any methyl groups or any carbons extra. So just the 6-carbon ring with the alcohol. So we know we need to bust that off, and we know we have to break either here, here, or here. We can leave that flexible, that left side. We can kind of decide where we want to break it a little later. It's just good to see your options. So one thing, this molecule looks a little crazy. What's something we can do to make it look less crazy? Let's just get rid of the epoxide right now. Let's just pretend, yeah. I'll put these down. Notice I made a cis double bond. That's important. What you have to do, you look at the epoxide and you see how the stereochemistry is oriented. This CH3 is on the same side as this CH. The 2 carbons are on the same side. So that means you need to go back to a cis double bond where those carbons are still on the same side. Up here, we have hydrogens. What reagent do we use to form those epoxides? MCPBA. Yep, MCPBA. Great. So this is a little easier. So the epoxide is it's a little much to look at. This is a little better. So we have an alcohol here.
It's not a normal benzene.
Oh, I'm sorry. Yeah, I just kind of instinctively went for the benzene. It's just a cyclohexane. Sorry about that. Yeah, it's not a benzene. Good catch. So this alkene piece. Alkenes are they're not useful if you're trying to form carbon-carbon bonds. What functional group would we want to use instead that might be more useful? About a triple bond. Yeah, acetylide. So we're going to have to take this back to a triple bond because we want to use that acetylide anion. We don't want that double bond there. We want a triple bond. So let's go ahead and take it down. H3C, C triple bond to a C. CH, OH, and our ring. Great. So we reduced a triple bond to a cis double bond. Remember before when we used the sodium or lithium metal with the liquid ammonia and the solvating electrons, that gave us the trans double bond. So how do we make a cis double bond? We talked about that one too. Yeah, we're going to use H2 and that poisoned catalyst, that Lindlar's catalyst. H2 with palladium and barium sulfate in quinoline. Awesome. So here we are back at our triple bond. Acetylide can attack what things? What things can acetylide attack to generate new carbon-carbon bonds? It can attack carbonyls. Yep, so it can attack some sort of carbonyl-containing compound. Hint, hint. The other thing it can attack are primary only alkyl halides. That can just SN2. So say you have your acetylide, negative charge, that can SN2 here. What would happen if you use secondary or tertiary? If you change that site to a more sterically hindered site, is SN2 going to happen anymore? No. What will happen instead? So this is a strong nucleophile in addition to being a strong base. It's going to do E2. So if you have anything but primary, you'll do an E2 reaction. So don't use anything but primary. That's the reason. Has to be primary. Looking here, we have our triple bond next to an alcohol. Remember we said we liked alcohols for carbon-carbon bond formation, right? And we can break the bonds immediately adjacent to those alcohols, right? That should be your general target. Breaking the bond next to an alcohol is great. So we're going to form a carbon-carbon bond here. If we form an alcohol, what are we attacking? What is the acetylide anion going to attack? It's going to attack a carbonyl-containing compound if you're going to form that alcohol. If you did what we did before, you have your acetylide anion with your primary alkyl halide, SN2, no alcohol. The alcohol is generated when you hit that carbonyl-containing compound. So we're going to use a carbonyl-containing compound because of that alcohol. So now we need to break this up. So see, we already drew the line where we're going to break it, and it's immediately adjacent to the alcohol. We have 4 carbons on this side. So it's going to be 4 carbons. And then 1 carbon with the ring. That's kind of our skeleton. How do we know where the carbonyl is going to go? The carbonyl is going to be on the side that holds the alcohol in the product. So see, so left or right to the line, is our alcohol to the left or the right of the line? It's on the right side of the line, so the carbonyl is going to stay on the right side. So our carbonyl is going to be on that carbon right there. I'm going to draw that a little nicer. And see, we have this hydrogen here. That hydrogen didn't go anywhere, so it's going to be an aldehyde. If it were an R group, like say you had another R group coming down here, you would generate a ketone instead. All right, so we've got that out of the way. And are we just going to put a Grignard on the left side? No, we're not going to use a Grignard. So we're already set up for the acetylide anion. That's powerful enough on its own. You don't need Grignard for that one. So if you're using the acetylide anion, that is your powerful nucleophile. If you don't have acetylide, you need to generate Grignard in order to make your powerful nucleophile. In this case, we don't need to make it. It's already given with the acetylide. Yeah, no.
You added carbon by mistake. Oh, no, you added carbon?
Oh, we added a carbon?
Yep.
Shoot, sorry guys. Yeah, there should be 3 carbons. I can't count. So carbon 1, 2, 3. So it'll be 3 carbons on the left. Sorry about that, guys. So we have 3 carbons on the left. What's that left side going to look like? We said it's not a Grignard. What's it going to be? Acetylide, right? H3, C, C, triple bond. We're basically going to draw that left side over again. And we're going to draw it with a hydrogen here, right? Right? No, not right. We want the ion, the anion, that acetylide anion. That's our powerful nucleophile. That's what we're going to use here. So we're going to add these 2 together. Mechanistically, what happens? That lone pair attacks the backside of the carbonyl and kicks that bond up onto the oxygen. What does that generate? A negative charge on the oxygen. So what do we do to resolve that negative charge? Then H3O plus. Then H3O plus. Yep, I'm going to go ahead and erase these arrows. All right, we're set to go there, right? Let's go ahead and work the left side first. So looking again, let's just check back in with what we're allowed. Cyclohexanol and alcohols or alkynes of 3 carbons or less. So looking at the left, we're really close, aren't we? So can we just use an alkyne? Yes. Yeah, you can use an alkyne. You're given alcohols or alkynes of 3 carbons or less. So we can actually just take this back to an alkyne. That's all we have to do. H3C, C, triple bond to the C. Now we're going to put the H. That's an alkyne. This is not an alkyne. Kind of is, but it's the ion. It's the anion, that acetylide anion. Now we have our alkyne. What reagent do we use to deprotonate that terminal alkyne? Yep, that sodium amide, NaNH2. What's the temperature? 150. Awesome. So we're done here on the left side, right? That's it. That's everything, right? Yes, right. I feel like I'm making second guess yourselves all the time now, but Yeah, so we have 3 carbons, and it's an alkyne. So it fits all of our criteria for a starting material. We're totally good. So let's go ahead and make the right side now. I'm going to move a little this way. Okay, so we have an aldehyde. What functional group do we need to get back to? We need to get back to an alcohol. Alcohols are the useful ones for synthesis. Also notice, do we need to shave off any more carbons? Yes, we do, yeah. So we're allowed cyclohexanol, but that doesn't mean that that extra carbon can still stay on there. We need to take that off. So we do need to do another carbon-carbon bond forming reaction. So we're going to want to go back to an alcohol. Alcohols are very useful. They're a pivot point for many carbon-carbon bond forming reactions. So if you're in doubt, get back to an alcohol. Like if you know you need to do more carbon-carbon bond formation, you got to get back down to an alcohol. That's the big thing. So what can we do to turn this into an alcohol? What reagent is going to turn this alcohol into an aldehyde? So we're oxidizing it, right? We're going to use one of our oxidizing agents. So our oxidizing agents are Jones, we have our dichromate, and we have PCC. So if you use Jones, let's use Jones here. What do you get if you use Jones on that thing? You get a carboxylic acid on there. Do you want a carboxylic acid? No, you want an aldehyde. Is there something else we can do to have it stop at the aldehyde? PCC. Yeah, that's the reagent you're going to want to use. You may also want to put it in DCM. I've seen on her old exams where she'll just say PCC, but it'll often show up in DCM. So that's kind of a useful thing you might want to throw in. So PCC gets us back to our alcohol. Now we're ready to do that carbon-carbon bond formation. And we're going to break the bond immediately adjacent to the alcohol, right? That's what we did before. We're going to go ahead and do that again. I'm going to put this in red. I'm going to break that bond. So which side, left or right, is going to contain our carbonyl? The left. Talk to each other for 10 seconds. Tell each other why the carbonyl has to be on the left. Ready, set, go. Talk for 10 seconds.
I just want to mention one thing. For the deprotonation, you don't have to indicate 150
I was
degrees.
thinking, yeah. Because
So
that's
you can
just for the
do that.
vicinal dihalide removal.
Exactly.
Yeah,
So you
cool.
clarify that, like, it's just like for forming a triple bond.
Cool. Sweet. Okay, so this left side has the alcohol on it originally, so that's the side that's going to be our carbonyl. How many carbons do we have on the left side? 1 carbon. So what's the only 1 carbon carbonyl compound that we have? It's going to look like this. Formaldehyde. 1 carbon carbonyl compound. And it's going to be on the left like that. Got him. So, do we use acetylide in this case? Did we have a triple bond anywhere? No, so we don't have our good nucleophile there, so we need to make our good nucleophile. What is that good nucleophile? Grignard. We're going to need to make that Grignard now, and that's going to be on the right because our carbonyl was on the left. It's where our oxygen is, on the left. So the carbonyl has to be on the left. Process of elimination puts the Grignard on the right. Is the Grignard connected, so the carbon, is it connected to bromine or magnesium? Magnesium, exactly. So you're going to want that magnesium directly connected to the carbon. Don't flip them. That's points off. Awesome. So mechanistically, that bond will come attack the backside of the carbonyl, kicks that bond up onto the oxygen. What does that generate? It generates a what? A negative charge on the oxygen. So what do we have to do about that? We have to protonate it, then H3O+. We have to protonate that positive charge to give us our alcohol. If we leave that off, you generate the alkoxide. we'll actually find out in Orgo 2, keep this in the back of your mind, that you may want to stop at the epoxide, or you may want to stop at the alkoxide. These are pretty reactive, so you may not want to use the H3O plus all the time. But if you want the alcohol, which we do, you're going to want to use H3O plus. Awesome. So we have formaldehyde and a Grignard. Let's synthesize formaldehyde real quick. What did we say about turning alcohols into aldehydes? What reagent? Remember, we had Jones dichromate PCC. It's PCC. PCC is the only one that's going to stop. If you use Jones, this thing is actually going to bust open into CO2 and water. It'll actually oxidize it so much that it'll just bubble away. So we have to use PCC in this case to stop at that aldehyde, to keep it from oxidizing further to CO2. Awesome. Are we done there? Let's double check. Alcohols or alkynes of 3 carbons or less. That is an alcohol, 1 carbon or less. So we're good. Can't be less than 1, but yeah, you get the idea. So let's go ahead and make this Grignard. What do you make Grignards from? It's going to be an alkyl halide. You're going to use magnesium and ether. I heard Dr. Bean prefers THF if you want to specify an ether. So Mg and ether, we have this Br on the cyclohexane. So we're just going to do Br2, light, and we have cyclohexane. We're good, right? No, why not? Yeah, check. Double check that you're getting to the right thing. Cyclohexanol. So are we allowed to go back to cyclohexane? No, yeah, don't do that. So even though that's a step you've done a bunch of times, and you're like, oh, shoot, I'm at the end. Like, I'll slap it on there and I'm done. Great. You know, you just lost some points. So just always be checking what you're allowed. So cyclohexanol. What reagent is going to turn an alcohol into the alkyl halide? PBr3. Why didn't we use HBr in ether at 0 degrees Celsius? Yeah, that would only be for tertiary. So here we use PBr3 because this is a secondary, and PBr3 works on primary or secondary. So now we're back to cyclohexanol. And that's the end. That's every piece. We have a little bit of extra time. I kind of moved through this pretty quick. I'm still going to go back to the nomenclature. Zoom out on this one. Does anyone have any general synthetic technique questions? Oh, do you still want to the temperature?
150, yeah.
Yeah, so real quick. It doesn't impact anything if you put it. So you can put the 150. It's not required. The 150 is only required when you are forming the alkene from a vicinal or geminal dibromide. So if you use NaNH2 on that to make your alkyne, 150 degrees Celsius required. I always put it to be safe because it's not going to like ruin the deprotonation if you put it. So I usually just throw it there. Just know it's not necessary if you're only using it to deprotonate. Awesome. Any questions about synthesis? I still am going to double back and do nomenclature, but we're still a little early, so just if anyone has general questions that you want to address all of us. Okay, so let's go ahead and double back and do our nomenclature section. All right, nomenclature. Very first thing, so it used to be that the very first thing was that we found the longest carbon chain. That was our job. Now our job is to locate the primary functional group. We have a new first job. So our first job is to identify the master functional group, if you will, the highest priority functional group. That's done by oxidation state. So looking at this first problem, we have an alkyne, we have an alkene. Which one has higher priority? They're tied. They're actually tied. Yep, so they actually have equivalent priority. And if you have a compound that has an alkane and an alkyne in it, it's going to be called an enine. So the alkyne will go last, so it kind of has a little bit of priority there, but functionally speaking, they're equivalent. They totally tie, so it's going to be an enine. Let's count how many carbons are in our longest chain that contains all of those bonds. So we have 1, 2, 3, 4, 5. We're definitely not going to go down here. 6, 7, 8, right? So we have 8 carbons. So it's going to be, and actually let's not write the parent yet. Let's go ahead and decide how we're going to number this. So we could number it going from the left to the right or from the right to the left. Let's look and see what that would give us. So let's go this top route, the left to the right. That puts us having a substituent on 2 and having a substituent on 3, 4, 5. Right, 2 substituents on 5. The alternative route has our double bond on 3. Our first point of difference has already been decided. That 2 wins. So that 2 is going to win. We are going to start from the left and go to the right. So this is going to be carbon 1, 2, 3, 4, 5, 6, 7, 8. Awesome. So we've numbered this thing. Let's go ahead and write out what our parent is. I find that to be useful. So how many carbons? There's 8 carbons, so it's going to be an oct or an octa, depending on whether we need diene, triene, any of that. So oct. And we said it was an enine, right? Octenine. But in the parent, we need to include the locations of those. So that actually has to be incorporated in with your parent. I know there's different ways to shuffle it around. I prefer this way, and I'll show you why. So our ene, is our ene our double bond or our triple bond? Ene is the double bond, exactly. So that's the one on 5, right? So we're going to say oct 5 ene. And where's the ine? 2. So 5 ene, 2 ine. There are different ways to rearrange the numbers. This is, I think, the best way, because if you're going to put the 2 ine, like if you're going to put the 2 by the ine, you might as well just stay consistent and do that the whole way through. Makes your life way easier when you're studying. Just put the 5 by the ene, the 2 by the ine. You're good. That, I think, is the simplest way to go about that. So we have almost all of this done. Do we have any other substituents to worry about? Yes, on 5 we have a methyl. Awesome, we're ready to name this thing, right? No, why no? What's up? Stereochemistry, yeah. Double check for stereochemistry. Make sure that there's nothing you need to do. Is there any stereochemistry about this triple bond? No, it just inherently doesn't have any. 180-degree bonding angles. So looking at this alkene, we may need to do E and Z stereochemistry here. The way you check if you need it or not, cut this double bond in half. And then what you do, you are going to look separately at the left side and the right side. You're going to see if there are 2 different groups on both sides. So look at the left side first. So we have, I'm going to go different color. Let's go green. We have those 2 groups there. Are they different? They're different. Let's look at the other side. Oops. And then we have a hydrogen here hiding. Are those 2 different? They're different. If you answer yes to both of those questions, if they have different groups on both sides, that's when you do E and Z stereochemistry. Let me just show you an example. Would you do E and Z stereochemistry here? No, you would not, because now these are the same. That's also why you don't need to do this on terminal alkynes, or terminal alkenes, sorry. You don't need to do that because you have 2 hydrogens on a terminal alkene, right? Those match, no E and Z necessary. But just keep in mind, it's not just terminal alkenes. Internal, you may also not need to do E and Z if it's like this, where you have those 2 identical groups. But that's not the case. So we need to do E and Z. What we need to do now, we need to assign priority to the left groups and the right groups. So let's just look at the left. What wins, the top or the bottom? The top, yep. Initially they tie. So initially you've just got carbon versus carbon. So then you have to look at what those carbons are connected to. This is H, H, H. This is C, H, H. First point of difference is this C, so the top is going to win. So we're going to call that top winning. Looking at the right side now, is the top or the bottom going to win? Yeah, top instantly. Awesome. We're going to get rid of this line in the middle. We're done with that line now. I would erase it. What you're going to do now, you're looking at cis and trans now. So look at the priority functional groups you selected. Are they on the same side or are they on different sides of that dotted line? They're on the same side. So does that mean E or Z? Z, the same side. So this is going to be Z, stereochemistry. If you have any questions about how to calculate E and Z, definitely ask, because it will probably be there. Do we need to put any numbers with Z? No, we don't, because there's only one site that has E and Z. There's only one site that could have E and Z. So you only need to tell people Z, because they'll be like, Z, okay, it has to be that one. There's only one. So you only just put Z. So we put our stereochemistry way out front, right? That's the first thing we do. Then we do our substituents. I can even write this out. Stereo, subs, parent. That's how they're ordered. So we now need to put the substituents. We've already included the alkyne and the alkene in our parent name, right? So now we just need to put the substituents. So we're going to put 5-methyl, oct, 5-ene, 2-ion. And that's that. If you have questions about that, raise your hand. And people will come, for sure. Okay, so moving on to this number 2. What was our first job again? What was the very first thing we had to do? We have to locate the master functional group. Yeah, we have to figure out the priority functional group. What is that in this case? The alcohol. Alcohols beat alkenes and alkynes and alkyl halides and alkanes. So that alcohol is going to be our master functional group. So we need to find the longest carbon chain that contains that group. It has to contain as many of our parent functional group as we possibly can. So we're going to go, it's definitely going to include this chain, right? So we have one going to the left, one going down. Which one are we going to pick? Doesn't matter. They are completely identical. Can you see that? They're 3 carbons, terminal alkynes, both of them. Completely identical. So you can choose either, just for the sake of keeping it nicer to look at. I'm going to go with the top, and the bottom will be our substituent. Next, we're tasked with numbering this thing. We're going to give the numbers that puts the parent functional group, the priority one, on the lowest numbers. So even though we could do this 1, 2, 3, 4, 5, 6, 7, 8, 9, like that, we're going to go the other direction. We want that alcohol to be on the lowest number possible. Looking back here, remember, the alkyne and the alkene were tied. They're tied for priority. So we have to decide from the first point of difference in numbers. We want to give the lowest numbers possible. In this case, there's no tie. The alcohol wins. So we want to give that alcohol the lowest possible number. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. What is the parent name of an alcohol? It's going to be all. It's going to have all at the end, OL. And how many carbons are in this thing? We have 9 carbons, so it's going to be non. So this is going to be an ine-all. And where are the numbers for that ine-all? So where's the ine? On carbon 8. It's all the way out on carbon 8. So we have a non-8 ine. And where's the all? 3. It's on carbon 3. So non-8 ine 3 all. That is our parent name. That takes care of this and this. Do we have any other substituents we need to worry about? We do. That equivalent one down there. So we're going to need to do some complex naming. How do we number substituents? We're going to start closest to the parent automatically. Even though starting the other direction would put the alkyne on the lower number, we're going to go directly out from the parent, starting from the carbon that is not the parent. So 1, 2, and 3. So 3 carbons, what prefix are we going to use? Prop, it's going to be propyl of some kind. Where is all of this whole substituent? Where is it on the parent? It's on 6. But we may need to use some numbers to describe what's going on just inside the substituent. So we're going to open up a parenthesis. Do we have any substituents in the substituent? We do. There's an alkyne here, and that is a substituent in this case. It's no longer part of the parent, so we need to identify it as a substituent. So we have prop. Where's the ines? We have prop ine be 2 ine. And you end this YNYL. So it's sort of like how you do like an ethyl or an alkyl with the YL. Even though it's ine, we're still going to end in YL. So prop 2 inyl. Just to reiterate, the reason I opened a parenthesis is because we're going to need to specify where the alkyne is. Right? We need to say that it's on carbon 2 of our substituent. We had to open the parenthesis because if we didn't put the parentheses, we would be trying to say that there was an alkyne on this carbon 2. We're not trying to say that, right? We're trying to say, hey, check this out. This just relates to the substituent. The 2 just relates to the substituent. That's when you use the parentheses. So we need to put those parentheses to say that we're talking about this carbon 2. So anything else we need to talk about before we name this thing? Stereochemistry, RNS stereochemistry. We're given these wedges and dashes. First thing you check, is it chiral? You may not need to do RNS. You may be given stereochemistry on a site that isn't chiral, and she may be trying to trick you. So we're going to check to see that this thing is chiral. How do you know if it's chiral? It'll have 4 distinct four distinct groups attached to it. So this ethyl is different from this long chain, right? Those 2 are different from the alcohol, right? And different than the hydrogen, right? So we have 4 different things attached to that carbon. So that means this is a chiral carbon, and since we're given the stereochemistry, we're going to need to do RNS here. Now we assign the priorities, and that's done by atomic number. So the highest atomic number atom is going to win. Which one has the highest atomic number? Oxygen. Oxygen is priority 1. What's next? Carbon. Carbon is next, but we have to break the tie. So looking, we have a carbon on the left and a carbon on the right. They're both carbons. They both are CH2s, actually, right? So are they identical? Yeah, the CH2s are identical, so we have to go one more. This is a CH2, this is a CH3. So which one wins? the CH2. The one on the left, the CH2 is going to win because this guy is connected to carbon, hydrogen, and hydrogen, CH2. This guy is just connected to 3 hydrogens. And that's it. So the first point of difference here is this carbon, so that's going to win. So our second priority is this left carbon. Third priority is the right carbon. Hydrogen is the worst of them all. So it's going to be on 4. Where do we want our lowest priority group to be, ideally? We want it to be in the back on a dash. Let's check. Is it in the back? Yes. So are we going to need to reverse our answer? No, we're not. So we're just going to keep our answer. Our answer is going to be just fine. Erase the 4. You're going to draw an arrow from 1 to 2 to 3. Is that clockwise or counterclockwise? Counterclockwise, so R or S? S. Yep, so this is S stereochemistry. So to start this name off, we're going to say 3S, right? No. No 3, just S. Because there are no R and S sites other than that one, other than the one on 3. So you don't need to tell them. There's only one possibility. So you just have S. And now we do our substituents. So we started with stereochemistry. Now we have our substituents. So 6, sorry, it'll be a dash, prop, 2, enol. Then we're going to say our parent name, non, 8, ein, 3, all. It's a long one. But you can see if you just work it systematically, just work the problem systematically, even though this is like a super long, terrifying name, doesn't really matter. Every bite-sized piece is totally doable on this thing. Awesome, here we go. Last one. So we have 3 alcohols here. So our parent functional group is going to be alcohol. It's not really competing with anything. Alcohol is automatically going to win. So the next task is to find the longest carbon chain with the highest number of that functional group possible. You're going to want to include as many as possible. Can we include all 3? No. So the maximum we can include is 2. So we need to find the longest chain with 2 alcohols. So let's look at the bottom chain. 1, 2, 3, 4, 5, 6, 7. And if we go up instead, we have 1, 2, 3, 4, 5, 6. So we're going to stay on the bottom, right? Because if we go up, we get a 6-carbon compound. If we stay low, go the bottom the whole way, you'll have a 7-carbon compound. So we could name 1, 2, 3, 4, 5, 6, 7, or we could go the other direction. Which one are we going to do? Doesn't matter. It's symmetrical, exactly. So it's completely symmetrical. We don't need to worry about that. So let's just pick left to right, make it easy. So how many carbons in our parent? 7, exactly. So this is going to be a hept of some kind. And this is actually a tricky one. This is specifically for diols. There's a little tricky rule here. So when you have a diol, you need to use the word heptane diol. You have to call it a heptane diol. That is just specific for diols. If you had 2 alkenes and you were using a diene, you would say, like normal, hepta, whatever numbers, diene. So this is just specific for diols. So we're going to have a heptane 1, 7. Oh, she puts it there. I don't care. Diol. I like them at the end. You can do either way. So alternatively, you could say 1, 1, 7, heptane, diol. I like the first way. So that is our parent, 1, 7, diol. Like that. Do we have any subs? Yes. So on 4, we have a complex substituent. So we're going to need to open up a parenthesis because we have to say where this oxygen or this OH is, right? Because it could be here. What if it were there? Like we need to specify where that's going to be. So where do we start numbering substituents? Connected to the parent. So right off the parent. So that's a little light. Let's try a different color. This could be 1, 2. That's it. 2 carbons. So what is this called? Normally it's an all, right? As a substituent, the name changes. So this is now called hydroxy. As a substituent. When it's a part of the parent, it's in this all, so you don't need to say hydroxy. And it's not hydroxyl, just hydroxy. So we're going to say that there is a hydroxy substituent on carbon 2. So 2-hydroxy. Notice we opened the parenthesis because we're not talking about that carbon 2, right? We're talking about this carbon 2. So 2-hydroxy. And then what? 2 carbons is what? Ethyl. Yep, 2-hydroxy ethyl. And that's all of our substituents on this thing. Any stereochemistry to speak of? None. So we're ready to roll. So let me just move this so it's out of our box. Get these numbers back. 3. Awesome. Okay, we're ready to go. So we're going to start with stereochemistry. There is none. So now we're going to go to our subs. 4 dash open parenthesis because we need to say this carbon 2 hydroxy ethyl. Close that. We're done talking about the sub. Now we have heptane 1,7-diol. And that's it. That is the 2018 exam. If you have questions, talk to Sabrina and I afterwards. We're here to help. I also have office hours Friday morning. So from 9 to 11 a.m. Friday morning, I have office hours at SEP. Does everyone know where SEP is? So the library building, if you're looking at the front, say this is the front of the library building. If you go around, you hit the UC, right? You'll see the student center. What you're going to do is take a left and go inside the library building from the back. Don't go in the front. So if you go around, go in the back, go downstairs, and there are signs that'll take you to SCP. And I have office hours there.
And I'll also have recitation tomorrow at 5:30 to around 6.